All right. Hi, everyone. If you haven't already, go ahead and pull up the notes for 4.1 and 4.3 in Blackboard so you can follow along. Oh, sorry, I jumped right into things. I hope everybody's well. These two sections deal with polynomial functions. We'll be talking about this some more next week and like how we deal with solving equations and that kind of thing. But basically, polynomials are just kind of extending stuff we already know. Like we already know a couple of examples. Linear functions are polynomials. So linear functions look like y equals ax plus b. Probably used to seeing that with an m instead of an a, but it doesn't matter. Quadratics that we've just been talking about, y equals ax squared plus bx plus c. I'm not going to write down the sort of generic version of what a polynomial looks like because it ends up looking sort of scary, but basically the idea is the same kind of thing, that you've got a bunch of terms added together. The poly part of polynomial is the Greek root for many. A bunch of terms added together where each term has whole number, like positive whole number powers of a variable x, and you've got real coefficients, right? So the default thing is to write them in like descending order. So we could have a degree 3 thing. Oh, yeah, sorry, degree. That's this, right? Degree is the highest power of x that shows up. So linear functions are degree 1, quadratics are degree 2, didn't write the 2, there we go, and so on. So we could have what we call a cubic. We've seen those before, but the sort of generic version of a cubic would be something like ax cubed, bx squared, cx plus d. Excuse me. Just like with quadratics, anything other than the highest, like in order for it to be degree 3, this term has to show up. Any of the other ones could be 0 though, like they don't have to be there. We're going to get into this a lot more, but that leading term, the degree, and what happens with that term that has the highest power, that's going to tell us a lot about how these things work. We've already seen that a little bit with the stuff we do know, linear and quadratics. So like, look at these two examples. We can tell right away by looking at them that, for example, this is a parabola and that it opens. Oh, can we do that Blue's Clues thing where I say like, which way does it open, or Dora the Explorer or whatever? Which way does it open? And then like I pause. And I'm assuming you all shouted up, right? It opens up because that is positive. So the same kind of idea that the leading term tells us a lot about what's going on is going to sort of continue to be a trend. So what I would like you to do is take a minute, pause the video, pull up Desmos or grab your calculator and graph these 4 things, and just kind of look at them, think about what they look like, see what you notice as you kind of work your way down the list. I would not graph all of them at the same time, like graph them one at a time and just kind of sketch what the pictures look like on the blank graphs there, so that you can get a sense for kind of how they're different and what happens as the degree. Because notice as we go down the list, the degree is increasing, right? This is degree 1. I'm going to start abbreviating that, 2, 3, and 4. Because again, that's the highest power that shows up. Okay, so pause the video for a second, graph those 4 things, take a look at them, see what you notice. And we're back. Okay, so first one, y equals 2x plus 1 is a straight line, right? Linear. Degree 1, it's got positive slope, right? Which tells me that it's sort of increasing, right? Like the ends are pointing, one up and one down. If you want to think about sort of placing yourself in the middle and looking at what's going on. But looks something like that. Crosses the x-axis there, has a y-intercept there. So that's some stuff we can say about that, just, kind of based on like the appearance of the graph. The second one, this is also something we're pretty familiar with, right? This is quadratic or degree 2 function. It's got a positive leading coefficient, right? Positive a value, right? Or leading coefficient, which means it opens up. So the ends are both pointing up there. It's got 1, 2 x-intercepts or zeros. Write that down, 2 x-intercepts, 1 y-intercept. We know more about quadratics, like we could find the x-intercepts if we needed to. But there we go. We'll just kind of talk about the shape of things and counting. All right, this one, degree 3. Degree 3 functions are called cubic. I might say that once in a while. It's not super important, but the degree is 3. The a term here is positive as well, right? So positive, I'm just going to start calling that the leading coefficient. If you want to call it a, that's fine. Again, that means that it sort of winds up pointing up, right? Now here, notice that like one end is pointing down and one's pointing up. There are 1, 2, 3 x-intercepts. And one place where it crosses the y-axis. Also, you might start to notice as you're going through these that like as the degree is going up, the graph is kind of getting more, complicated, right? More interesting, maybe that's a word that's a little less charged. More stuff is happening, right? Like first one, you got a straight line. The second one, has like a curve to it, right? It turns around somewhere. This one actually turns around twice, right? There are 2 places here and here where it sort of changes direction. And then this one is degree 4. Again, not super important. That's called quartic. Like quarter or quart or whatever. Anyway, degree 4, positive leading coefficient again. Y'all think I'm fun in class. Wait till it's 10 p.m. and I'm recording a video while my kids are sleeping. Positive leading coefficient. There are just 1, 2 x-intercepts, but there are 1, maybe 1, 2, 3 places where it changes direction. 2 x-intercepts, not 4, 3. We'll call those turning points. But I mean places where it goes from, sort of decreasing to increasing, right? Those points that are at like the bottom of a, dip or the top of a rise, kind of like the vertex for a quadratic, except there's more than one of them. Okay, so again, just kind of generally, as we go down this list, as the degree goes up, the graph gets more involved. There's more stuff happening. Excuse me. That pattern does pretty much continue in general. The higher the degree, the more things can happen. The way these things are all related kind of is what it looks like. So I think maybe this would be a good one to look at for starters, because we're most familiar with these because we've just been talking about it for a week, 2 weeks. week and a half. I don't know. Time is meaningless. Anyway, degree is 2. It changes direction one time. One turning point, right? That's the point that we call the vertex, right? And we know how to find, but there's one place where it changes direction, right? It goes from decreasing to increasing, if we think about reading left to right. And there are 2 places where it crosses the x-axis, 2 x-intercepts. So things to notice would be the way that these things are all kind of related to each other, right? So keep that in mind, and then take a look at the other 2, the degree 3 and the degree 4. So pause the video again for a second, take a look at those, see if you can see kind of the same relationship. So hopefully you came up with something like, well, this one's got degree 3 and 3 x-intercepts and 2 turning points. So far it looks like those 2 things match, and this one's one smaller. This one is degree 4. It's only got 2 x-intercepts, but 3 turning points. So one of those things kind of matches the same rule, but there are only 2 x-intercepts, right? When we might be expecting 4, if it's going to work the same way as the previous couple did. But keep in mind also with like quadratics that we know the most about, they don't have to have 2 intercepts, right? We've seen some like, this, where they don't have any real solutions at all, right? They have like complex roots. So it doesn't have to have any at all. It can have fewer than that. It just can't have any more than 2, right? Because the shape of the graph, doesn't matter how you move it around, you're never going to find a way to make it cross the x-axis more than twice. So looking at this, you can kind of imagine, hopefully, how if I took a thing that looked like this, right? It's kind of shaped like a W. If I took a thing that was kind of W-shaped like that, and maybe I set it right there, that there would be 1, 2, 3, 4 x-intercepts. But no matter how much I move that around, and the shape of the thing is, that's the part that's kind of determined by the degree, right? It's like capped, like how complicated or how much twisting and stuff it can do is kind of limited by what the degree is. So there's no way that I could take that thing and move it around and find it crossing the x-axis any more than 4 times, right? There's 4 there. I can get fewer. I can have 3 or just 2, but there's no way to make it cross more than 4 times. So that's pretty much how we kind of sum all this relationship stuff up. If a polynomial has degree, whatever, what that does is give us a limit, right? Then we know the limit or the maximum amount of stuff that can happen. Looking at it now, I'm not sure why I just wrote out exactly what I said, but if we know the degree, then what we know is kind of a cap on how much stuff can happen. Like a thing that has degree 2 can't have more than 2 intercepts, but if the thing has degree, 5, it can have 5, or it could have 4, it could have fewer than that. It just can't have any more. All right, so let's take a look at a couple more examples. And all this stuff here at the bottom of the first page is just kind of summarizing like what we just did. So, kind of fill that in a way that makes sense for you. But so what I can tell by looking at the equation for a function is basically the thing I want to start by looking for is the leading term. Leading term is the biggest one. Normally that's going to be the thing that's in front, but they don't have to be in order. Typically we like write stuff in descending order, but it's the biggest one, wherever it is. So looking at that, the degree is 3. Now, if I actually graph the function, y equals x cubed minus 2x, yeah, x cubed minus 2x, we get something like that. This has 1, 2 turning points, right? Don't worry about the coordinates, just there are 2 places where it changes direction, there they are, and 1, 2, 3 x-intercepts. Again, don't worry about the coordinates for right now, just there are 3 places where it crosses the axis. 3 x-intercepts, 2 turning points. The end behavior, we mean like what do you can't see what I'm pointing at, what do the ends of the graph do? Like not the stuff in the middle, but if I were going to, draw this on paper and put little arrows at the ends of the thing, how would I draw them? These go like that. One up and one down. Or they're pointing in opposite directions. Okay, now again, you take a minute, go graph the rest of those things, and then, come back and kind of fill stuff in. But that has degree 4 and 4 intercepts and 3 turns, and the ends both go up. This one is written in factored form. So to figure out the degree, we got to think about it a little bit. We're looking for what would the leading term or the biggest term be if we multiplied everything out. I don't want to multiply everything out because that's going to be a big giant mess. But I can figure out what the leading term would look like by thinking about what would happen when I multiplied it out. The leading term, the one with the highest power, would come from the like the first part of that product, right? It would come from when all those things hit. So the leading term would be x to the 5th. Now there's a bunch of other stuff, and I don't know what it is, but I don't need to know either, because this tells me what I need to know at the moment. The degree is 5. There are 5 x-intercepts, there are 4 turning points, and the ends go like that. So we've looked at examples of stuff from degree 1, 2, 3, 4, up to 5. And in every case, what we've seen with the end behavior is that when the degree is odd, the ends point in opposite directions like this. The same thing was true for the straight line. And when the degree is even, they point in the same direction. Think about quadratics, right? Parabola, degree 4 stuff, the couple that we've looked at, you got kind of a W-shaped thing. So let's kind of add that to our list. Degree. We learned stuff about number of x-intercepts, number of turning points, and end behavior based on whether the degree is even, you're going to go the same direction, or if the degree is odd, they're going to point opposite directions. Okay, so take a look at this first question. If a polynomial has degree 7, that's the only thing we know about it. And how many x-intercepts and how many turning points do you think it'll have? And what do you think the ends will do? Again, pause the video for a second. Think about answering that question based on like what you've seen so far. We don't have a specific function here to graph or anything, just a thing has degree 7. What do you think it's going to do? Okay, so the number of x-intercepts can be up to 7. It could be fewer. Could be fewer. Can't be more. So it could only have 6. No way it could have 8. Turning points up to 6. And same idea. Because again, degree gives you a cap or a limit on how much can happen. The end behavior, though, that part is kind of locked in. The ends are gonna point in opposite directions. I'm gonna do the end behavior by drawing little arrows like that. If I were standing in front of you right now, I would, hold my hands up and point and stuff. Y'all know me at this point. But basically, like either like that or like that, right? So there's going to be some twisty turny stuff in the middle, but the ends would end up looking like that. If we ask the same question about a thing that had degree, I don't know, 8 is even. So x-intercepts, it could have as many as 8. Turning points, it could have as many as 7. The end behavior, both ends will point the same direction, either both up or both down. Because again, that part is based on whether the degree is even or odd. Okay, so you should be able to answer number 2 then. If a thing has degree n, I might do 2 things, say if n is even or if n is odd, then what happens? I'm gonna work smarter, not harder here. There we go. Up to n, up to 1 less. That part just depends on n, but if n is even, then the ends are going to point in the same direction. If n is odd, they're going to point in opposite directions. Okay, so that kind of sums everything up, right? So number 3 there, summarize what you've learned, discovered. In class, you all would have been doing a lot more of this, but that doesn't really translate that well to video. So just, somehow kind of summarize that for yourself in a way that makes sense to you. All right, now what I want you to work on are these 2 problems. So determine the degree and the end behavior of the function, find the zeros and state whether it crosses the x-axis or touches the x-axis and turns around at each of those, and then use that information to sketch the graph of each one. Let's take a look at A together. Y equals negative 2 x minus 4 squared times x minus 2 times x plus 2. Before we jump into that, think again about like what the degree would be here, right? X squared times x, and there's a negative 2 out in front. So I'm not going to multiply the whole thing out, but the leading term would look like negative 2 x to the 2, 3, 4, from where sort of the highest term, the highest power of all those, from when that part happens in multiplication, right, in the like giant mega FOIL thing that's going on, the biggest term that would show up is x to the 4th. Then there's some other stuff that I don't care about so much, but that means the degree is 4. And the leading coefficient is negative. If the degree is 4 and the leading coefficient is negative, what do you know? This is another one of those Blue's Clues moments where you shout it out. Right. Yeah. You know that it's degree 4. So it's going to, have that kind of like W shape sort of thing going on, maybe. And the leading coefficient is negative. So it's opening down. So both ends are going to point down. And then we've got, I guess, sort of an upside down W, which most people call an M. If we look at the graph, that's kind of what we get. Right now, I know it doesn't look like it now, but if I do some stretching of the thing, there you go. You can kind of see that, shape. It's sort of lopsided. It's real tall on one side, not on the other so much, but there you go. Okay, now all the stuff that we wanted to find, make myself some room here. The degree and end behavior. Okay, so degree is 4, both ends are pointing down. Find the zeros and then describe what happens at each of them. Okay, well, finding the zeros, I've got the graph, so I can do those just by looking here. Zeros or x-intercepts are the same thing. I'm going to start working in a little bit more, calling them zeros of the function, but the zeros are -2 and 2 and 4, just the x coordinates, right? And then what happens at each of those is that the function crosses at -2, and it crosses the x-axis, and it crosses the x-axis at 2. And at 4, though, it touches the axis and turns, or it kind of bounces off, right? Looking back at the equation of the thing, we already know about solving by factoring, right? And we know that finding zeros or finding x-intercepts means setting it equal to 0, right? So basically we're asking, like, if I take this thing and set it equal to 0, what solutions do we get? Well, it's already factored. So if it's factored, the zero product property still applies. So you would set this equal to 0, which gives you x equals 4. And you would set this equal to 0, which gives you x equals 2. And you would set this equal to 0, which gives you x equals -2, right? So it's just like a big giant, factored quadratic. There's just more pieces, right? But I would still set them each individually equal to 0 in kind of the same way. What happens is that you get these things, right? So this one goes with this. Do this. Here we go. Those go together. And those go together. And those go together. So can you tell by looking at them what the difference is in the fact that 2 of those go through the x-axis, right? They cross it. The function, just goes right through. And at one of them, excuse me, at x equals 4, instead of crossing the axis, it just touches at that one point and kind of bounces off or turns around. Well, what's different about the factors? Right, hopefully you yelled out something about the fact that this one shows up twice, right? That one's squared. That means that you've got 2 factors that look like that, x minus 4 times x minus 4. The other ones just show up once, right? The one's usually not written, it's just kind of understood, but they show up one time instead of 2. That's called the multiplicity. So multiplicity, that's how many times those factors show up, right? It's that power on the individual factors. What that tells you about is this, how it actually behaves at the 0. If the multiplicity is odd, it's going to go through. If the multiplicity is even, it's going to sort of bounce off or touch and turn around like that. If it's odd and bigger than one, that kind of changes what the shape is. But the idea, again, is really just that odd means it's going to go through, even means it's going to bounce off. You can tie that back to like quadratic stuff if you want. The having that even power, squaring it, that means that you're going to have the same sign on either side of the place where it's zero. That's why it bounces off like that, or appears to bounce off like that. Okay, so what we're going to be looking for then is kind of taking something like this and being able to sort of spell all that stuff out, right? So being able to identify all of those different things, or going from a graph. So like if I give you a graph, like, let me just draw a thing. If I say, here's a thing, it's a polynomial, and everything is sort of, nice, or like things happen where they look like they happen. What can you tell me about it? Well, those go the same way. So the degree's got to be even. It changes direction in 3 places. Let's see, ends same, turning point, turning points. There are 3 of them. There are 1, 2, 3 zeros. And one of them right here bounces off the axis, right? Which means it's got multiplicity 2. So what this all tells me is that since the ends point in the same direction, the degree has to be even. And if it's got 3 turning points, the degree's got to be at least 1 bigger than 3. And if it's got 3 zeros, the degree's got to be at least 3, but actually one of them has multiplicity 2. That means it kind of counts twice. So this all tells me that the degree must be at least 4. And you'll see stuff in the homework that'll talk about, like, if it gives you a graph like this, it'll say like, find the minimum degree. Well, it's got to be at least 4. Because that the multiplicity counts for it as well, right? So kind of putting all those things together, it's got to be even. It's got to be bigger than 3. It's got to be, 3, but one of those has multiplicity. So it's sort of, 3, but like with an asterisk, that one of those really counts twice. So all that stuff together tells me that the degree must be 4. Okay, so that's kind of the overview, right? The idea of things. I'm going to assign some problems, starting with this one, but check your email for other like details about things. I'll post an announcement about it as well. But I'm going to assign some problems so you guys can, kind of get a feel for things. And then we will, I would guess at some point need to, talk about this kind of when we're in person again. But any questions that you have that come up as you're working on stuff, please just let me know. And yeah, we'll go from there. So hope you all stay safe. Like I said, if there's anything I can do to help you, just let me know. Thanks.